Good morning, students. Um, we were discussing about atomic structure. By the name itself, you can make it out. And actually, in the previous classes, we started our journey with atomic structure. And the journey began with the what we have already read in our junior classes, and that was a basic recapitulation, followed by the new things or the more slight in-depth study of those things what we have read in the previous classes were discussed. So our journey began with that we discussed about the discovery of the electrons, protons, neutrons, followed by the Rutherford's atomic model coming into existence, with the slight modification later on was done by Niels Bohr in the Rutherford model itself in order to conclude or in order to give a more clear picture about the atomic structure within, whether that means the structure of an atom from inside. Now, regard after that, after that the discussion continued, or we have already discussed that the electrons were present, as mentioned in the specifically regarding the Bohr's atomic model, that there are electrons that are present in definite orbits and they are revolving around the nucleus. And these orbits are rather also called energy shells or energy levels, and they do not radiate energy. They're having fixed energies. So electrons are also having fixed energies until unless they're being disturbed or being forced to change their energy levels. And how much energy these energy levels are having, or how much energy a particular electron is having, that is also being that was discussed based on the equation given by the that's basically called as the energy equation of the electron, or the Rydberg's equation. And Rydberg's equation, then we discussed that one also, that R multiplied by 1 by n1 square minus 1 by n2 square, where n1 and n2 belongs to the first, the initial orbit and the final orbit levels, the energy levels. And basically, the energies over here we are described in terms of wave number, or the centimeter inverse, or the units were in inverse, not in joules, right? So all these things, and we started discussing regarding the different corresponding with how these energies correspond to different, what should I say, the different energies of the light as well. So considering the Vibgyor, how the Vibgyor can be correlated with the energies what the electrons are having, corresponding to each individual electronic proportion, or rather transitions. So we started our journey and we were going ahead, and we continued up till that part. So we will continue more with that later on. But today we will slightly take our different, we'll take a detour, and we will try to figure it out, that these electronic transitions or energy levels are these, when we are saying these orbits are having electrons, what is the distribution of the electrons within the orbit itself, and how these electrons are distributed, and where can we get these the electrons within the space available inside the atom. Now, to understand these, or rather to answer these questions, the first thing we need to know about the first theory important for this particular to answer these sort of questions, that is Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is actually the answer for those questions which just now I raised, or that was, what are the questions? That are these, or what within the atom itself? Within the atom itself, there is an empty space. Then how the electrons are distributed, or where they are actually present? Are they present throughout? Is it a continuous? Are they present as a continuum in a continuous way? Or they are scattered? Or they are basically present in a one particular place? Or different energy levels are within that energy levels, how they are present, arrangement, each and everything. Mostly, the first thing that was these questions were preliminary or the first were answered by Heisenberg. So the Heisenberg uncertainty principle states, we need to know the statement first. It is not possible to determine simultaneously the position and momentum of a moving microscopic particle with absolute accuracy. Now you may ask, what's the relation with that one? My question was how they're distributed, and are they present in one particular place, or they're continuous, or they're scattered? Now, before answering, that means our question is basically regarding the what's the position. We want to figure out the location of the electron. We want to figure out the location of the electron. But Heisenberg stated that it is not possible, as per the statement says, what the statement says, which is not possible to determine simultaneously the position and momentum of a moving microscopic particle with absolute accuracy. What does this statement mean? This statement means that if we are trying to accurately determine the exact position of a microscopic particle, since we are now discussing about electrons, so since we are having electron with us, so what we are going to do, or what's our attempt is, our attempt is to exactly determine that where this particular electron lies. What is the particular electron lies? Whether it's lying at let's consider at a 45-degree angle, or whether it's if there are multiple electrons present, then all are having probably an angle of 30 degrees between each other. So, and they're having a distributed with a gap of 30 degrees. What is that? Now, that we are trying to exactly locate, to point out where a particular electron is. But unfortunately, since electrons are in motion, they are not stationary, they're in motion. So since they're in motion, so we will not be able to identify at what the exact position is with accuracy. The question is about accuracy. So we will not be able to identify the exact location of the electron, since electron is already under motion. So either of the one is possible. So if we want to locate the exact location of a particular particle, microscopic particle, with accuracy at a very instant time, right now, for example, right now, where is this particular electron is, then we will not be able to identify that. With accurately, we cannot say this. But parallelly, now if we want to measure, see why we are not, if you want to measure the velocity of the particular electron, then definitely the exact location of the particle becomes impossible. So with accurately we cannot say that. That is the meaning of the uncertainty principle. And that was basically an attempt to answer that problem, that where an electron lies. So either of the one is possible. Now, since we are considering the uncertainty principle, and Heisenberg stated that, so based on a mathematical relation, Heisenberg concluded this. So the mathematical relation, okay, I'll come to the mathematical relation later. Let's move on to explain this one in a more elaborate way. Here, there are two fans you can see. One fan is rotating, another fan is stable. Rather, not stable, I should say. Another fan is not rotating. So one is having rotational motion, that's under motion. One is stationary. To be more accurate, precise about the word stationary. The first question is can you determine the velocity of the fan? can you determine the velocity of the fan? That means the first one. With respect to the first figure, a picture which you can see, the fan which is having rotational motion, can you determine the velocity? If yes, you will say yes, definitely, sir, we can determine the velocity. That what's rotational speed, rotational velocity of the fan. Excellent. And if you can rather determine the rotational velocity of the fan, then now can you tell me how many blades the fan is having? Or if the fan is having 3 blades, then at which point right now the third blade of the fan is located? So can you report accurately how many blades the fan is having with respect to the first picture? Or how many of the fan is having 3 blades, that at which point right now, at the very instant, the third blade is? Similarly, if I move on to the next figure, that fan which is stationary, can you determine the position of the blades? Of course, yes, we can determine the position of the blades. Now, accurately can you determine? Exactly, we can determine with high accuracy that this is the position of the blade. No doubt about that. What's the velocity of the fan? Can you tell me? That's uncertain because the fan is stationary, so it's having no velocity. So, what's this velocity of the fan? Uncertain. Whether it's having a very, maybe possible, what our sensory, what we are seeing with our naked eyes, is basically the blades are stationary. But maybe it's the reality is not. It's moving at such a rather it's such slowly that the displacement our naked eyes are not being able to identify. So such displacements also we are actually physically what we are seeing is at the fan blades are stationary. So with accuracy we cannot say that what the velocity is and what the position of the or velocity of the fan is, but we can say accurately or accuracy what the position of the blade is. So this is what the basic of Heisenberg's uncertainty principle. So it is because so it's uncertain. So it's uncertain that we will be able to determine both velocity as well as the position with high accuracy. At the same time, it's not possible. Mathematically, this Heisenberg's uncertainty principle is represented by delta x multiplied by delta y, p, that means the product of the delta x and delta p, greater than equals to h bar by 2, where h bar is actually h by 2 pi. Now what is h? Delta x is the uncertainty in the determination of position. Delta p is the uncertainty in the determination of the momentum. H is a Planck's constant and h bar is a reduced Planck's constant. Okay. Now this delta x and delta p in somewhere, some places or some books or some rather there you can also find it out that instead of delta x and delta p, they've actually written as if sigma x and sigma p. So since delta x is basically the uncertainty or the change, how much it is, the difference, what we are saying. So uncertainty is actually delta is actually uncertainty means how much the difference is. What is the difference? How much you are sure? So if the uncertainty, the delta x value is less, very less, that means we are very sure. But if the delta x value is more, so that means my uncertainty is much more in comparison, rather with respect to in determining the position of the particle within the space. So it's the same thing. So uncertainty in the determination of the momentum. So this is another form. That means nothing else. That momentum is basically, we know that it's mv. So since m is constant for a particle itself, so the change will be noticed or will be recorded for the velocity. So delta x delta v greater than or equals to h by 4 pi m, where delta v is uncertainty in the determination of the velocity. Velocity of the velocity of the particle. Now, the question arises that why we need to study this uncertainty principle. Why? Only just to improve our general knowledge. Is it so? The answer is no. The answer is no. Why we need to study this one? Why we need to study? The uncertainty principle plays an important role in many discussions on the philosophical implications of quantum mechanics. That means uncertainty principle formulates or rather makes the way towards quantum mechanics. This uncertainty principle plays a very important role in discussing many quantities, many parameters of quantum mechanics. So, for this reason, uncertainty principle is important because it gives answers to certain questions of the quantum mechanics. And this uncertainty principle also is one of the foundation stone of the quantum mechanics. Another important rule is to carry out quantum experiments. To carry out quantum experiments. What sort of experiments? Testing of number phase uncertainty relations in superconducting or quantum optic systems. This is one type of experiment. Another one, that means in superconductors, testing of superconductors. It's also applicable for quantum optic systems, where we have learned we know what optics is all about, but this is quantum optic systems. So to carry out experiments, uncertainty principle helps. Another one is extremely low noise technology required in gravitational wave interferometers. Low noise technology, where basically low noise means disturbance. Another is it's an energy, it's a wave, you can say it's some sort of frequency. With low noise technology, that means minimum, very less disturbance present. Or so such issues where there is very low disturbances are there, and we need to figure out certain informations from there. So uncertainty principle is highly important over there in carrying out the experiments based on low noise technology in gravitational wave interferometers. Now, what information? Point is now, why suddenly Heisenberg came up with this uncertainty principle? So previously we had that question was asked, why we need to study uncertainty principle. We have understood that why we need to study uncertainty principle. The next question is coming up, that why suddenly Heisenberg came up with this uncertainty principle. Was Heisenberg mad? Suddenly he came up with this uncertainty principle. What forced him to suddenly propose these sort of uncertainty? That means which is not having no certainty, lack of certainty. There are some principles or laws or hypotheses like this. What compelled him to do so? Now, in order to answer these questions, it is necessary to understand the problem whose answer is uncertainty principle. Okay, so in order to answer this question, it is necessary to understand the problem whose answer is uncertainty principle. So obviously, what is the problem? You need to know that what was the problem? The problem was actually created by Louis de Broglie, a French physicist. That problem was actually created by Louis de Broglie. And if I'm not wrong, you have heard the name of this person. De Broglie or Louis de Broglie, you have heard the name of this person, right? So he created this problem. What was the problem now? Still I haven't answered. Yeah, it is going on. We are in the darkness. What was the problem? Okay. Louis de Broglie came up with this remarkable discovery known as wave-particle duality of matter. Now, another problem. We are already now looking around for the problem whose answer was on that Heisenberg's uncertainty principle. We are searching for that problem. We haven't got that answer. Now another question coming up, another problem is wave-particle duality. Now, what is this? God. Okay, let's check it out. What is wave-particle duality? With Einstein's idea that light, though it's a wave, but depicts particle character also, with Einstein's idea, again, that light, though it's a wave, but it depicts particle character also. And the particle character is basically due to whether it comes out, or it gets reflected with the help of photons, which are packets of energy, which are packets of energy. Now this is something. Now this idea just turned the stone around. It created a revolution. That light, that still that time light was considered to be a wave, and and suddenly and suddenly wave, it is showing particle character. Now particle character means it will have mass. Particle character means it will have mass, some size. So those are particle natures. So light is a wave, which is energy. It reflects wave character. Now it's having a particle character. Oh my God. But Einstein's idea was not only an idea. Einstein basically also later on proved that light was having particle character. Now, after listening to or after going through Einstein's work, and basically there was a story sudden that Einstein that De Broglie was having rather going through the work of the Einstein, rather this work about Einstein, that Einstein has concluded that light is a wave but it's showing a particle character. So he was also listening to the discussions of the other scientists of that time, that they were also were confused regarding this latest discovery. But since it was Einstein's theory and it was Einstein's concept, as followed by he was proved also, so they were accepting, but not full-heartedly. Suddenly, de Broglie came up with his own idea that if wave can depict particle character, then particle will also depict wave character. So de Broglie came up with another idea, which was basically an extension of Einstein's work, that if a wave reflects particle character, then a particle should also reflect wave character. Now this concept of this idea was totally rejected, and he was totally cornered that by everyone regarding this idea that particles, we are very difficult way of by way by which we're accepting this fact that wave is having a particle nature. And now suddenly de Broglie, he was telling that he was of the opinion that wave particles should have wave nature. Now de Broglie was basically, this was, I'm telling a small one, de Broglie was basically not actually a scientist initially, or rather a physicist initially. He was an historian. So he did his graduation and all this stuff in history and some sort of political science and administration. So he was a student of history. But later on with this, he carried on, he started his research work, that he wanted to prove that if wave can have particle character, then particles should also have wave character. So he did a lot of hard work, and in the year 1927, it basically thesis work, his PhD thesis work, where he proved that wave was basically, but rather particle can have wave character. If wave can have particle character, then particle can also have wave character, wave nature. So it will behave as a wave. That de Broglie's work was supported, laid the foundation stone. So de Broglie's work laid the foundation stone of the present day mechanics, wave mechanics rather. And his idea was if a particle of mass m and the velocity v, then it should have a wave whose wavelength will be lambda, wavelength will be lambda, and can be calculated by this equation. That lambda de Broglie's wavelength is h by p, where h is the Planck's constant and p is the momentum of the particle. Basically, h by mv mass is the mass of the particle and v is the velocity of the particle. Planck's constant, that is. Now, this de Broglie's idea, as I said, that it was basically later on in the year 1925, 1920, before 1925, that Einstein accepted de Broglie's concept or hypothesis. Later on in 1925, G.P. Thomson, uh, he proved by his diffractometric experiments and also by Schroidinger, both of them confirmed that de Broglie was correct. Now, this de Broglie's equation is also having an additional factor, which was not there in the previous equation, and that is that additional factor is the actual de Broglie's equation, that is h by mv into 1 minus v squared by c squared, where v is basically the velocity of the particle and c is the velocity of light in vacuum. Now, with certain approximations, or if it's also possible that if v is very less than c, then equation 2 transforms to equation 1. That means de Broglie lambda de Broglie equals to h by mv. Now we cannot neglect this v, h by mv. We cannot neglect that v from there, because since it's very, very small, the inverse will be very, very big. But over there, since it's very small, so and it's in the numerator, so the square of that one with respect to c, the entire answer will result out to almost equal to 0. So if v is very, very less than c, equation 2 transforms to equation 1. Now, as I said, now with the dual nature of electron coming into existence, a problem arose. With dual nature of electron coming into existence, a problem arose. Now that same thing, the problem. What was the problem? It imposed some restrictions on the simultaneous determination of the position and velocity of the particle accurately. Now, since when this dual nature of electron coming into existence, dual nature of particle coming into existence, it imposed a restriction that the velocity of the particle and the location of the particle, measurement of that one at the same time, became difficult. It's not measurement at the same time became difficult. Accurate measurement. Be very, very specific about that. Accurately is mentioned over there, accurately. So with accuracy, it became difficult to determine that what is the position and the velocity of the particle. So both cannot be, if it is having a velocity, for example, of 50,000 kilometers per second. Now it is having a velocity of 50,000 meters per second, so it will not be, so we cannot accurately determine what the exact position of the particle right now at the very instant. So either of the one is possible. Either we will determine the position accurately, or we will determine the velocity accurately. Either of the one. So this was the problem, that we cannot measure that one. And Heisenberg came up with that solution. And that is now you have understood, I hope, that what was the problem and what is the solution. So Heisenberg later on stated with that problem that we will not be able to measure that. We will not be able to measure that one, and that is the uncertainty relation has been given by delta x, the product of delta x, and that is uncertainty in the position and the uncertainty in the momentum is greater than equal, or rather is greater than equal to h bar by 2. Now, de Broglie's hypothesis was confirmed by G.P. as I said, G.P. Thomson's electron diffractometry experiments and Schrodinger's equation. Now comes Schrodinger's wave equation. Schroidinger was basically a German physicist. And he also in 1926, or yes, almost, that he proposed the wave equation. Wave equation, because de Broglie was having the wave form of the particle, and the wave equation was proposed by Schrödinger. Now, what the wave equation is? Schrödinger's wave equation. Schrödinger's wave equation is this. It is read like this way. This is grad square, or you can also say del square. So del square psi, this is this is trident shaped symbol is psi, psy. So del square psi plus 8 pi square m by h square multiplied by e minus v psi, e minus v into psi equals 0. Where this del square is actually, it's an operator, it's a mathematical operator, or it's a differential mathematical operator given by del 2 del x2 plus del 2 del y2 plus del 2 del z2. So del square equals to del, it's a three-dimensional operator. So you can see x, y, z, so it's a three-dimensional operator. So del 2 del x2 plus del 2 del y2 or plus del 2 del z2, where I is basically the wave function of a particle at a certain position in space. Wave function means wave function is an equation. Function is basically an equation. So it's a wave equation. So since the particle is showing a wave character, so definitely it should possess some sort, it can be represented in a mathematical form. It should have an equation. Mathematically, it can be represented. So that mathematically, it's a wave function. So where within this position, within the space, so certain position in space. Space means the vacuum or the space within the atom. So outside the nucleus, boundary till the boundary of the atom, that available space is focused on. So within that area, within that space, three-dimensional space, what is the equation by which the particle is following, the electron is following, and showing a wave character? M is the mass of the particle. A is the energy of the system, the total energy of the system. V is the potential energy of the system due to an electric field. V is the potential energy of the system due to an electric field. So since electrons are having their charged particles, we normally say that we consider that they are showing a charge. So positively charged, it's a negative charged particle, whatever it is. So it's a charged particle. So within that one, it's a potential energy of the system. H is the Planck's constant, and as I del 2 is del square, right? As del square, it's a Laplacian operator. It's also known as the Laplacian operator. The wave equation 3 turns into a more general form of Schrödinger wave equation. It's a more compact and a general form of Schrödinger's wave equation. It's given by h cap psi equals to E psi, where h cap is called the Hamiltonian operator given by minus h bar square by 2m into grad square plus v. So if you ask how this one is coming, it's not so difficult. You can just derive this one. So consider that equation, and if you put the value of h, and if you can re-alter the positions, if you can re-alter the positions of those of the equational parameters, you will get this form, rather this operator over there, or rather this h bar square by 2m to grad square plus v. Okay, so just you have to rearrange the equation, that's equation 3, and you will get this form. Okay. Now coming to what is the meaning of the wave function psi and psi square. Both are having different meaning. What's the meaning of this psi? Psi is basically the amplitude. Psi is, as we said previously, it's an equation, but actually that equation, since it's a wave, so definitely it should have an amplitude. Since waves do have amplitude. So psi is basically actually in more detail, it actually reflects the amplitude of the wave produced by the particle of mass m. And what is psi square? If I squaring it, psi square, the meaning is basically the probability. So since if we are having an amplitude, that means if we're having a curve, if you know the Gaussian distribution curve, so the central part is having the maximum, the highest probability. Now if that one is squared, definitely that area will get double. So that will give us the information that's the maximum that particular position will have the highest probability of finding an electron within a particular space available around the nucleus. Now, acceptable solutions of the Schrodinger wave equation provides information about those regions within the available space of the around the nucleus where the probability of finding the electron is maximum. So, acceptable solutions. You just be careful because it's written acceptable solutions. So I mentioned acceptable because there can be solutions which becomes unacceptable. Because if the probability and the situation and the answers turn out to such that there are minimum chances of finding an electron, then definitely those regions and those solutions will be rejected. And hence, acceptable solution provides information about those regions within the available space around the nucleus where the probability of finding an electron becomes maximum. The space is termed as orbital. That means the space where the electron will have the maximum chances of finding an electron, that is termed as orbital. I haven't written orbit, I mentioned orbital. Now, what are the conclusions from the wave function? What are the conclusions? The probability of finding electron at the nucleus is 0. So we'll not have any chance of finding electron within the nucleus. Now the probability of finding electron increases as we move away from the nucleus, and the minimum distance where we can get this chance of finding electron, that is 0.53 angstrom, and this distance basically corresponds to Bohr radius, which actually corresponds to basically reflects the radius or rather of an hydrogen atom. On moving further away from the nucleus, the probability of finding an electron decreases and becomes negligible beyond 2 angstrom, so 0.53. So just figure it out and just think about it and get one thing clear. So whatever the orbitals or rather the orbits we are having, we are familiar with the term orbits, and now we will switch over from orbits to orbital. Now, whatever the orbits and the orbitals we're having, those are present within 0.5, or rather found within 0.53 angstrom to 2 angstrom. Now, what are the results from the wave function? The most probable distance of finding an electron is 0.53. So this distance corresponds to the presence of the first orbital within the first orbit. So we are familiar with the orbit. But where this first orbital is present, the orbital is present within the first orbit. And that orbit or the orbital is termed as S orbital, where S means sharp. On moving further from the nucleus, the probability distribution curve provides information about further orbitals with respect to the within the respective orbits, and along with the S orbital, we will also have p orbital. P stands for principal. D orbital. D stands for diffuse. F orbital. S stands for fundamental. Now, S orbital is having a capacity of 2 electrons. P orbital having a capacity of 6 electrons. D orbital 10 electrons, and F orbital 14 electrons. Now, the number of electrons in a particular orbital was also obtained from the probability distribution, where the probability distribution provided the information about the orientation of the orbitals within the three-dimensional space. Orientation of the orbitals means it gives an information about the shape of the orbital. It gives an information about the shape of the orbital. That means the orientational orbitals within the three-dimensional space. So such information was a tremendous breakthrough into quantum mechanics when the quest or the greed or the thirst and the need of identifying a particular electron came up. So now we are moving towards from orbitals. We are eager to know about the shape of the orbitals. We are eager to know if we can. Now we can figure it out. Every orbit, every electron which is present inside the orbital accurately or not. Thus, a complete solution of the wave equation gave three numbers or parameters. What are they? The principal, symbol N, azimuthal, symbol L, and magnetic, symbol M. These numbers are basically quantum numbers. These numbers are basically quantum numbers which will help to designate a particular electron. So all the electrons will have their individual principal, azimuthal, and magnetic quantum numbers. But when the reality was determined, still it was these quantum numbers was failing to specify a particular electron, and thus spin quantum number S with a symbol was introduced. So with these quantum numbers, when they were unable to completely specify an electron, the spin quantum number was introduced. And this was introduced basically first this concept was proposed by there was a physicist named Ralph Kronig. Yes, he was the first one to give this proposal, Ralph Kronig, about the spin quantum number. But before we study about the quantum numbers in more detail, it is important that we should have more information about the orbitals. So before going into the quantum numbers, which are actually are slightly more detailed information about the electrons and other orbital levels, orbitals also, we need to have a little bit more information about the orbitals. And these orbitals information, so we need to focus first on the shape. And we need to focus first on the shape. What the shape? S orbital is having a spherical shape, something like this. You can see it's a spherical shape. So that means, so the electrons present within S orbital will have a uniform electron density around the nucleus. Uniform, that means wherever you'll go, it will have a same electron density or electron cloud, uniform electron density electron cloud. Because such small things we will not be able to figure out exactly with our microscope that where the one electron or two electrons are. So what we will see is we will see a charge, an electron cloud-like image will come up. So it will be a uniform around same the electron density electron count will be uniform throughout the nucleus. P orbital is having a dumbbell shape. So whether since S being a spherical, so whether since it's a three-dimensional space within the atom itself, so the three dimensions you can see x, y, z. So the x, y, z will have three dimensions, and we since it's a sphere, so all the directions will have the equal distribution. But what about this dumbbell shape px, py? Dumbbell shape p orbital. It will have different shapes or different orientations. So we will have individual p orbitals in individual directions. So one along the px, that means along the p orbital along the x direction, p orbital along the y direction, p orbital along the z direction. So it's termed as px, py, pz. Then we are having the d orbital. It's a clover shape. D orbital having the clover shape. How it looks like? Three-dimensional space, d orbitals reflect 5 different suborbitals. So p is the orbital, px, py, pz, they are suborbitals. S is having no suborbital. D orbital is orbital, but D is having 5 suborbitals. What are they? dxy, dyz, dzx, dx square minus y square, and dz square. So these are the 5 suborbitals of d orbital. And f orbital, no information about the general shape of the f orbital because they are having 7 suborbitals. F is having 7 suborbitals, and still the exact shape of the suborbitals is under research. So still it's not clearly defined that what is the exact shape of the suborbitals of F orbital. Okay, so with this, I'll like to stop over here with the shape of the orbitals, and I'll continue with the orbital, or the quantum numbers, and more information about the quantum numbers and orbitals in the next class. So and till then, take a very good care of yourself. Stay safe. Thank you. We'll carry on with the next class. Okay. Bye bye. Take care.